Have a nice day, everyone. So, I am Rose B. Diaz from Bisabitri, and I would like to present the deflection of beams moment area method and the bending moment diagram by parts. So, the first one is the moment area method. So, the moment area method is useful for determining the slope or deflection of beam at a specified location. It is a semigraphical method in which the integration of the bending moment is carried out indirectly using the geometric process or the properties of the area under the bending moment diagram. As in the method of double integration, we assume that the deformation is within the elastic range, resulting in small slopes and small displacements. So, the moment area method is one of the most effective methods for obtaining the bending displacement in beams and frames. In this method, the area of the bending moment diagrams is utilized for computing the slope or the deflection on the particular points along the axis of the beam or frame. Moment area theorems. We will now derive two theorems that are the basis of the moment area method. The first theorem deals with slopes, the second theorem with deflections. So the first moment area theorem is the change in the slope of a beam between the points is equal to the area under the curvature diagram between those 2 points. The statical or first moment of area, or Q, simply measures the distribution of a beam section's area relative to an axis. It is calculated by taking the summation of all areas multiplied by its distance from a particular axis, or area by distance. The first moment area theorem shows the elastic curve AB of an initially straight beam segment. The deformation has been greatly exaggerated in the figure. As discussed in the derivation of flexure formula in section 5.2, two cross-sections of the beam at P and Q, separated by the distance dx, rotate through the angle of D relative to each other. Because the cross-sections are assumed to remain perpendicular to the axis of the beam, is also the difference in the slope of the elastic curve between P and Q, as shown in figure 6.4. From the geometry of the figure, we see the dx equals to P, where P is the radius of the curvature of the elastic curve of the deformed element. Therefore, the derivative, which is upon the using moment curvature relationship. So the first moment area theorem states the total change in slope between A and B is equal to the area of the bending moment diagram between these 2 points divided by the flexural rigidity L. So for the solution, substituting the equation, we obtain 1 bm minus 1 BGA. So team right hand side of Q is represent the first moment of the shaded area of the MJ diagram in figure 6.5. About point B, denoting the distance between B and the centered C of this area by x minus 8. So, we can rewrite the solution. So, this is the second moment area theorem. That the first moment area represented by the right hand side is always taken about the point at which the tangential deviation is being computed. Do not confuse the tangential deviation of JJ with respect to A with IAJB, tangential deviation of A with respect to B. In general, these two distances are not equal, as illustrated in Figure 6.5. So the first pictures shows above the slide. So the positive deviation is it located above reference tangent. So the second one, negative deviation, is B located below the reference tangent. So the third picture shows us positive change of slope in counterclockwise from left tangent. So the right side it shows as tangent at B and tangent at A. So what is sine convections? The following rules of sine, illustrated in Figure 6.7, apply to the moment area theorems. So what is sine conventions? A sine convention is a choice of the physical significance of signs, plus or minus for a set of quantities. In a case where the choice of sign is arbitrary or the general, a sign convention is a special case of a choice of coordinate system for the case of one dimensions. The moment area method of finding the deflection of a beam will demand the accurate computation of the area of a moment diagram, as well as the moment of such area about any axis. So we can apply to the two moment area theorems by the following rules. For the first one, the tangential deviation or BFA is a positive of B lies above the tangent line drawn to the elastic curve at A and negative if B lies below the tangent line. The second one, positive OJJ over A has a counterclockwise directions, whereas negative OTG over A. Then the third one has a clockwise directions. So the next slide, which is the bending moment diagrams by parts. So the application of the moment area theorems is practical only if the area under the bending moment diagram at its first moment can be calculated without difficulty. The key to simplifying the computation is to divide the bending moment diagram into some simple geometric shapes like rectangles, triangles, and parabolas that have known areas and oxytoroidal coordinates. Sometimes the conventional bending moment diagrams lends itself to such divisions, but often it is preferable to draw the bending moment diagram by parts, which is part of the diagram representing the effect of one load. So the shear and bending moment diagrams are analytical tools used in conjunction with structural analysis to help perform structural design by determining the value of shear force and the bending moment at a given point of a structural element such as a beam. So the construction of the bending moment diagram by parts for simply supported beams proceed as follows. So the first one is to calculate the simple support reactions and consider them to be applied loads. Introduce a fixed support at a convenient location. A simple support of the original beam is usually a good choice, but sometimes another point is more convenient. The beam is now cantilevered from this support. To draw a bending moment diagram for each load, including the support reactions of the original beam. If the diagrams can be fit on a single plot, do so drawing the positive moments above the x-axis and the negative moments below the x-axis. So the shear force diagram point of inflections is where the sign of the shear force in shear force diagram changes. Basically, it means the beam doesn't carry any shear stress at that point. The point of contraflexure is the point where sign of bending moment changes. Shear and bending moment diagrams are analytical tools used to conjunction with structural analysis to help perform structural design by determining the value of shear force and bending moment at a given point of a structural element such as a beam. Only the last step of the procedure is needed for a cantilever beam because a fixed support is already present. As an illustration, consider the simply supported beam of ABC in figure 6.8. We start by computing the support reaction. The results are shown in the figure 6.8. We introduce a fixed support at C and show the reaction at A as applied load. The result is cantilever beam, the statically equivalent to the original beam, that is the cantilever beam has the same conventional bending moment diagram as the beam in figure 6.8. Now, draw a bending moment diagram for each two loads as shown in figure 6.8. So the moment due to A is positive, whereas the benefit of constructing the bending moment diagram by parts becomes evident when we compare 6.8 and D. The former contains two simple parts. A triangle and parabola. Not only is conventional diagram harder to divide into simple shapes, but also before this can be done, the maximum bending moment at its location have to be found. As mentioned previously, the fixed support can be introduced at any location along the beam. Let us draw the bending moment diagram by parts for the beam in figure 6.8 by placing the fixed support at B as shown in figure 6.8. So this location is not convenient as C, but is served as illustration. As a result, we have transformed the original beam into two cantilever beams sharing the support at B. The applied force consists of both the original reactions and the distributed loading. Therefore, the bending moment diagram in figure 6.9 now contains the three parts. As note that the moments of the force about B are balanced. In the other words, summation of MB of R equals to summation of MB of L. So it is represent the sum of the moments of the force to the right and to the left of B, respectively. When we construct the bending moment diagram by parts, each part is invariably of the form M equals to Kx raised to m, where n is a non-negative integer that represents the degree of the moment equation of table 6.1 shows the properties of areas under the M diagram for n equals 0, 1, 2, and 3. This table is useful in computation required by the moment area method. So this is the table of plot of M equals to k x raised to n. So the bending moment, or BM, is a measure of the bending effect that can occur when an external force or moment is applied to a structural element. So the concepts is important in structural engineering, as can be used to calculate where and how much bending may occur when forces are applied. So that's all. Thank you.